Welcome to The Explainer. Today, we're going to unravel a massive geological mystery together. We usually think of a volcano's life as this really straightforward story. It erupts with all this fiery fury, eventually runs out of fuel, goes completely quiet, and then, well, it just dies. But what if I told you that the silence on the surface is actually completely lying to us? Today, we're exploring the double life of volcanoes, and we're looking at the incredible hidden role that water plays in all of this. Because water is really the secret agent here. It can keep a volcano's fiery heart beating deep underground, and eventually, it can literally erase a massive mountain right off the face of the Earth.
So let's just start by challenging a basic assumption that I think we all make. Can an extinct volcano actually still erupt? I mean, if a mountain hasn't made a peep in hundreds of thousands of years, we naturally just assume the show's over, right? The fire's out? Well, recent discoveries are actually forcing geologists to completely rewrite the rulebook on volcanic lifespans. Let's see why.
Section 1. Secrets of Extinct Volcanoes.
So to really wrap our heads around this, we're heading to Greece, specifically to a mountain called Mathana, which is about 50 kilometers outside of Athens. Now, to the naked eye, it looks completely dormant. As humans, we typically classify a small volcano like this as extinct if it hasn't erupted in the last 10,000 years. And sure, 10 millennia seems like forever to us, but geological reality operates on a vastly different scale. When scientists looked really closely at the rocks from Mathana, they found these tiny microscopic minerals called zircon crystals. Now, these crystals only form in magma chambers deep underground. And what they revealed proved that even while humans thought the volcano was completely dead, a massive pool of magma was actually growing silently, just out of sight.
Okay, let's dive into this 700,000-year history because it's fascinating. The first period of eruptions ended about 280,000 years ago. Then, there was this massive quiet period, over 100,000 years, where absolutely nothing erupted. Finally, around 168,000 years ago, a second period of eruptions began. Now think about it. If the volcano was truly dead during that huge middle gap, there shouldn't be any new zircon crystals forming, right? But scientists found the exact opposite. The absolute highest amount of zircon generation happened exactly when the mountain was completely quiet on the surface. So it wasn't dead. It was just holding its breath.
Section 2. Magma's hidden waiting game. So how is this even physically possible? How can liquid rock just sit stalled beneath the Earth for 100,000 years without turning into solid rock? Well, the answer lies in a hidden ingredient, and that is water. Specifically, what geologists call water-saturated magma. Deep underground, under just incredible pressure, water mixes right into the magma. And this water acts almost like a chemical preservative. It helps keep the magma completely molten and stops it from freezing into solid rock. That's what gives this seemingly dead mountain a beating heart.
Resvin Gabriel Papa, a volcanologist over at ETH Zurich, actually has a brilliant way of explaining this. He says, it's like a fizzy drink. We open the bottle and shh, all the gas comes out. And I love that because it makes the geochemistry so easy to visualize. The magma is essentially the soda, and that intense deep earth pressure is the cap on the bottle, just keeping everything mixed together perfectly. So let's break down Papa's fizzy drink analogy step by step to see exactly why the magma stalls out instead of erupting. First, the magma tries to rise toward the surface, and as it does, the surrounding pressure decreases. That's like unscrewing the cap on that soda. Second, because that pressure is lower, the water that was keeping it perfectly molten suddenly bubbles out as vapor. Third, and this is really the critical moment here, without that water, the magma immediately begins to crystallize. It becomes incredibly thick, viscous, and just sticky. It literally becomes too thick to push its way out of the ground, so it just stalls, trapping itself safely beneath the surface.
Now, you might be wondering why should you and I care about magma stalling out? Well, because this fundamentally changes how we assess danger. Think about it. If a volcano hasn't erupted in 10,000 years, we might not even bother monitoring it. But if its magma chemistry is just playing this long, drawn-out waiting game, these supposedly extinct volcanoes could actually be totally unmonitored threats to coastal populations and cities. So, understanding this deep Earth science has a very direct, real-world impact on human safety.
Section 3. Sculpting the volcanic surface.
Okay, so we've seen how water hidden deep underground stalls a volcano. But water falling from the sky, that actually dictates how the mountain will age and eventually be destroyed. We can see this transition perfectly by looking at two Hawaiian islands. Take the Big Island, for example. It's a young shield volcano with a smooth, largely undissected surface. Now compare that to an older Hawaiian island like Kauai. Kauai is about 4.1 million years old, and it is substantially dissected, just completely carved up with massive, deep river valleys.
Now, you might wonder why young volcanoes, like the ones on the Big Island, are so smooth in the first place. Well, it's because of a really interesting phenomenon known as the 500,000-year lag. When a volcano is young, its basalt lava rock is incredibly porous. It's highly permeable. It acts exactly like a giant geological sponge. When it rains, the water just sinks right into the ground to recharge aquifers. It doesn't pool on the surface to form rivers. So because of that, it takes a massive lag of roughly 500,000 to 2 million years before the rock changes enough for real surface destruction to finally begin.
And to prove this timeline, researchers actually zoomed out to look at the massive global scope of this phenomenon. They analyzed 97 different oceanic islands from all over the world. And these islands range in age from just 500 years old all the way up to over 10.7 million years old. By looking at such a huge data set, scientists could finally start to map out the universal rules of exactly how volcanic islands are erased.
Section 4. Water, the Great Eraser.
So, we know there's this lag time while the island acts like a giant sponge. But once that sponge fills up, the local climate really steps in. When researchers chart out the degree of an island's dissection against both its age and the local precipitation, a very clear transitional period emerges. Somewhere between 500,000 and 1 million years old, islands in high precipitation regions start to erode and dissect significantly faster than those in drier environments. So basically, rain acts as the ultimate accelerator for erasing the mountain.
But here's the catch. It's not just about the amount of rain, it's about the intensity. There's a stark contrast here. Take the Galapagos Islands, which often experience these really gentle, low-intensity fogs. That water just gently infiltrates the soil without causing any major runoff. But contrast that with the Cape Verde Islands. They experience torrential, high-intensity monsoon rains. Even though they have a dry season, when those monsoons do hit, the sheer violence of the ephemeral rivers rapidly carves steep canyons right into the young rock.
So let's just run through the geological checklist of how an island actually gets erased over millions of years. First, as plants grow and rocks weather, soil develops, which naturally reduces that initial sponge-like permeability. Second, windblown dust starts acting like grout, just clogging up all the tiny pores in the lava. Once the ground is finally impermeable, the third step kicks in. Surface runoff concentrates into flowing rivers, and those act like chainsaws, cutting deep into the rock. Finally, massive chunks of the island's flanks can collapse right into the ocean, creating these steep cliffs and waterfalls, known as nick points, that actually erode the island even faster from the outside in.
And to really hammer this point home, let's return to Kauai. This is perhaps one of the most stunning examples on Earth. This single island, which is roughly 50 kilometers across, has an incredibly steep rainfall gradient. The dry side gets maybe a half a meter of rain a year, while the peak plateau gets an astonishing 9.5 meters of rain. And the data shows that the long-term erosion rates, the actual physical erasure of the island, are perfectly and positively correlated with exactly where that heavy rain falls.
Once again, let's bring this back to why this matters to us today. This multi-million-year dance between rock and water isn't just abstract geology. The way these islands erode completely sets the template for their entire ecosystems. It determines where the steep cliffs are, where the fertile valleys lie. And, most importantly for human communities living on these islands right now, it dictates exactly where they can reliably drill for fresh, sustainable groundwater.
So, we've seen how water plays this absolutely incredible dual role. Deep underground, a lack of water vapor causes magma to stall and hide, making really dangerous mountains appear totally dead for 100,000 years. While above ground, falling water acts as this grand sculptor, spending millions of years completely erasing those very same mountains from the map. And I think it leaves us with a pretty provocative final thought to ponder. If a supposedly extinct volcano is really just holding its breath deep underground, which dead mountain out there is going to exhale next? Definitely something to think about next time you look at a quiet peak. Thanks for joining me on this explainer. I really hope you found it as fascinating as I did.